volumes of solid disks and washers. We're going to start with disks today and move on to washers later. Here's the sketch of the graph. X and y axis, f of x and y of x. And we have a function which goes like so. Y equals f of x. But we only need it from a to b. And we know that this area can be found via integration. Now we know it's actually area between two graphs, which is area between f of x and y equals 0. Or we used to call it area below the graph. So if we take this area, which we know is the integral from a to b, f of x dx, that's the area, A. But now what if we take this area and revolving about x-axis? Nice American notation, which I learned, is this notation, revolving. You could see it from their graph. They have it this way. Doesn't matter. So we're revolving about x-axis. Now, here it is. You can still see it. This is a 2D shape that was revolved, got revolved. Here is how we're finding it. We're finding it through vertical slicing. From f of x to 0. From f of x to 0, now we're revolving it and it creates a 3D object. So it means that it will be connected through the area between graphs, how to find the volume of this object. Let's figure out how to do that. We will be using approximations. But what kind of approximation we should use? So originally, that's actually a very interesting idea here, check it out. Originally we used rectangles like so. Now, if you put those rectangles in 3D, it becomes a disk. And by the disks, I maybe imagine a coin. It's a coin. We're going to call it disk, because that's how books calls it. And we're going to call it a sample disk. Here it is. It's a circle, but it has a thickness. Here is the thickness of it. So, if it has a thickness, I will make it look like so. And now it looks like a coin. They call it a disk. And this is a sample disk because they will all be different. This is a sample disk. Sample disk is somewhere in the middle or just anywhere, doesn't really matter. Here it is with a width. It's a coin. This sample disk tells us how the shape looks like approximately. If we put lots of coins all over the place of this 3D object, which looks like a vase, then it will approximate the vase with a 3D object, which is a coin or a disk. I imagine coin. So now you have a stack of coins on top of each other, if you kind of imagine vertically. They're coins, and they approximate the vase, and you say, you see, all those coins have different heights, which means they have different radii, because the bigger radii, the wider they are. So it's a better approximation because I see it's overestimating or underestimating, but it will give you approximate shape of the coin. And it will look like so. There will be this wide one at the bottom. This is the coin number 1. Then it gets wider, coin number 2. Then it gets wider, coin number 3. Then it gets a bit smaller and then smaller. At some point it gets wider again. That's a bottleneck, I guess. Like so. And then it gets wider again. Something like this. You see, so I did approximate it. Here it is, see? That's my approximation of those, we're using coins. Again, human being nature, you take things you know and you use those things you know to approximate something you don't know. You guys concentrate. Thank you. So now let's find that sample disk. Let's find the volume of that sample disk, and then we're gonna find the volume of all of them, and the approximation happens here. This has radius r, right? We need to find the volume of the sample disk. The volume of the sample disk will be height or width of this disk times the area of this disk. The area of the base. The area of the base is a perfect circle. So height will stay as h, and then how to find the area of the circle? Who remembers the formula? Pi r squared. Pi r squared. That's the area of the base. We know radii, and the radii will be different. All the radii will be different. So we're going to use it in the formula there. Now we're going to stack them on top of each other, and then we'll have the same height, the same h for all of them. We want to use the same coins, they will be just bigger or smaller, but we want the thickness to be the same. Exactly like we used to have with rectangles. You want to keep something the same. In this case, it was delta x or delta y. Now we're going to have this h to be the same for all of the sample disks or all the disks. So let's write it down. Let's take V and then add or sum, right? All the sample disks. All the sample disks. Where? And let's explain what is happening here. H will be the same, and it's either delta x or delta y. Depends on the case. Case 1 versus case 2. Are they standing or lying down? That's what is the case here. And I will teach you how to distinguish between cases. But the whole point is adding them up together means having a sum. Sigma sum of those volumes of disks. Volumes of disks. That is what's happening here. Now, if you have just 5 disks, the approximation will be odd. If you have 10, it's a bit better. 100, a bit better. 1,000,000, even better. Blah, blah, blah. Limit of number of disks going to infinity of the sum creates a perfect volume, which is integral, and we know how it works. So to write it down, it will look like so. V equals sum of V sub I, right? I goes from 1 to n. That is the idea here. But we know now what V is. Let me put in another color. V is the volume of all of those disks. So it's going to be a sum, and we're going to plug a formula inside. Pi, well, let's do H first. H, pi r squared. R is changing with the V. Each V has its own R, so we're going to call it I. I is going from 1 to n. This is what's going on. This is how we're creating volume through integration. Again. And to make it perfect, we're going to send n go to infinity. Let n go to infinity. That creates a perfect integral. And this is the formula, which is V. Okay, maybe I should actually write it down. It becomes, so let's see, before, let's not put equal sign, let's put approximately, like so. Approximately. Before it was not exact. It was kind of ugly vase with the approximation of the coins. Let's make it equal, and it's a big deal to put equal sign. You have to be careful where you put equal sign. V is a limit of those sums. H, pi, r squared, where I is from 1 to n. So if I have 100 coins, I have 100 different radii. But then I want to have infinitely many coins. That is a definition of the definite integral. That is a definition of a definite integral, which is integral from a to b, let's put it in red, from a to b. Now, we're still going to have those sums. Actually, let's do this way. We're still going to have those disks over here. Pi r squared dx. And that is the formula we will need to remember. V equals integral from a to b pi r squared dx, or V equals integral from c to d pi r squared dy. Put those two in the boxes, and I will make a point right now about this. Actually, let me put like so, in yellow boxes. The difference is about the case 1 versus case 2. If you choose case 1, then you will use vertical slicing, which is, again, sounds so complicated. I never would recognize what this word vertical slicing is. Basically, your coins are standing, so they're vertical, right? In this case, we use dx, and radii will be in terms of x. If you choose case 2, then coins will be lying down, and then r radii will be in terms of y. So all the integral should be in terms of y, and that's why it's going to be from c to d. And here's the picture. This is, let me increase, representative disk is what they call sample disk. Sample disk. Here it is. And then the more you have, the better representation is. How to know if it's case 1 or case 2? We did explain you that it's top minus the bottom function, but there's one way of also to remember it. How thick this disk is. Is it thick on x-axis or thick on y-axis? Which basically means its thickness is a shadow on the x-axis, and shadow officially is called projection. We're going to do it in calculus 3 quite a lot. The shadow is on the x-axis or y-axis. Let's see. Here's how thick it is. And when I make this this point, I would not call it a point. When I make this blue situation, idea, interval, yeah, it happens to be on x-axis. So it is dx. Since it's dx, it's case 1. See? So that's how we're going to do it. This is case 1. Or you can remember, if they're standing vertical, it's vertical slicing. Vertical slicing is case 1. If situation is happening like so, how thick is this sample disk over here? Let's see. Oh, it's y thick, right? Here it is. It's y thick. So it's dy. Boom, case 2. So that's how you also can know it. But in general, you can see it's from right to left function situation or from top to bottom function situation. From top to bottom, like so. Finally, this is a beautiful picture. If you did not like my pictures, you don't have to copy this because it's exactly what we just wrote. It's not new. But if you did not like my pictures, here's the beautiful copy-paste pictures. To find the volume of a solid of revolution with a disk method, use one of the formulas below. Horizontal axis of revolution is pi r squared from A to B. And vertical axis of revolution, which is pi r squared from C to D. The first one is dx, the second one is dy. Make sense? In general, I'll keep re-mentioning the formula. We'll have 2 more formulas after this next week. So pi r squared, that's how you should remember. It is area inside of the integral where the thickness is dx or dy. Check it out again. Pi, I like to kick it out of the integral as well. Pi is outside. R squared. So pi r squared is area. So where is my thickness? Where did my thickness go? We had it h. Where did it go? Do you know? It is exactly dh. That is width or thickness of the disk. That is my h. How high the disk. So that's where it did go. It went to dx part, just like with rectangles. All widths of rectangles were the same. Same here. We assume coins have the same width. Now it looks like that. You see how thick is this coin is. dx. Sometimes people call it delta x. In general cases, we will teach you why in calculus 3 more rigorous. And that's why I know it's case 1. Case 1. But if the coin looks like so, and then how thick it is. dy thick, then it's case 2. Does it make sense? What do you think? Is it like too much talking or not too bad? And let's see. Let's write down the problem. And then I think we will finish it next time. But it's nice to have it written. Example 1. And then the more examples I will show you, the more confident you'll become in this. The most important problem you have to be good is sketching graphs. Find the volume. So all those problems have lots of writing in English, which I don't appreciate. Well, it's all applicational problems, you know. Thank you to engineering department to create all of these problems for us. Find the volume of the solid of the, well, we don't have to do the here, revolution. Revolution is not the revolution of the country. It's revolution by revolving. Just letting you know. Revolution obtained by So you see it's not bounded by, obtained by, whatever. Revolving the 2D region, nobody says 2D, just region, 2D region, and now it's bounded by, BDD by. So I will not be writing this down all the time. It's exactly the same question, literally all this time. Find the volume that was created, the volume of this solid that was created by revolving the region. What region? Region will be in 2D, and it's going to be revolving. Bounded by x, no, it's this one. Y equals square root of x, comma, x-axis. Oh, we're having something new now. X-axis, and at x equals 9. This is not enough information. This creates a 2D object, but how this object will be rotated comes down. About. This is a new information. About x-axis. And it not necessarily can be an axis. It can be another line or anything else. So actually it becomes pretty complicated at some point. Let's sketch the graph for you to imagine the situation. Solution. Step 1. Sketch the graph. Sketch which graph? 2D graph or region. Because then it's going to be 3D at some point. And now check it out. The previous chapter you have supposed to be good in sketching graphs to find the area. Now it's getting to next level. We're going to be revolving it to creating 3D object. Y equals square root of x. Hopefully you remember how it looks like. Goes through 0, doesn't go down because y cannot be negative, and it's growing like so. Sign it. What is x-axis? How to call it as a function? Y equals to 0, thank you. Y equals to 0 is the floor. So here it is, or just x-axis. You don't have to overcomplicate, but it's nice to know. And x equals 9. What does x equals 9 look like? It's a vertical wall. Find 9 somewhere on x, or just fix it. And now you have a wall. X equals 9. Right? So hopefully you're good at this. Check out my video if you're not. I'm kind of reviewing all this there. We created a 2D region from this information over here. And now we're rotating it about what? And it can be anything. So it can be anything. Let me again make a very clear point. This is the area between graphs. You can choose case 1, case 2 to find this area. But now we're revolving it. We're revolving it about x-axis. This is American notation. Have to warn you, you might not see it in all the books. But this is the rotation about x-axis. Look how to do it in 3D case, which is pretty cool. That is step 2. I'll put it here. Rotate. Rotate to create a 3D picture, plot, whatever. 3D plot. Plot? Is it plot? Picture. Bless you. So, to rotate it, you copy the region in 2D. Check it out how awesome it is. You copy it more or less, just imagining x-axis as a mirror, right? Like so. And then you make it look nice, so your brain right now doesn't see it as 3D. It looks flat. To trick your brain and make it look like a 3D object, create at least 2 circles, one at each end, for example, like so, or one at the end and one somewhere in the middle. See? Now your brain sees this as an object in 3D. So it's pretty cool. Our brain just needs this kind of volume imagination through either shadowing or circling. This is a 3D object, and we're asked to find the volume of this 3D object created from rotation of 2D object. What do you think about that? Isn't it cool? I feel like this will be pretty interesting for most of you because it has some creativity of drawing things. Lots of colors will be involved. From where to where we're working, from 0 to 9. What are the functions in 2D? Square root of x, y equals 0, x equals 9. What are the functions 3D? Well, now it's a 3D object. Is it hollow? Is it solid? Is it filled in? Or it has a hole inside? Next week we're going to learn what to do if it has a hole. What is going to happen if it has a hole like so? How the volume will change? It will decrease because now there's like a tube inside. We will have to find how to figure out that situation. And that creates cool ideas. Not only can be rotated about x-axis, it can be rotated about y-axis, and we don't draw this because it's a different example. Exactly the same picture rotated about y-axis will be completely different. Look at that. Copy, create 2 circles to make yourself visual that this is a 3D object. Well, that's a different object now. Moreover, it has a hollow piece inside. How are we going to figure this volume now? And it can be rotated about any other line, even tilted one, maybe rotated about this. Or what we're going to do in this class, let's rotate it about some kind of other line. Exactly the same object, say like so, exactly the same 2D object we just had from 0 to 9, and now you're rotating it about some other line. See? Now there's a hole over here. If this is 10, now it's empty inside. How to find that situation? So it becomes very creative from an engineering point of view and mathematical point of view and physical point of view, because after this, we're gonna make it heavy. We're gonna fill it in with chocolate, and we're gonna make a fountain out of this and ask you to find how much work was done to fill in this with chocolate or take the chocolate out of this object using a fountain. And that's where all this is going. Applications of integration. That's exactly chapter 7. How can we use all this information to find some cool stuff with gravitational forces, viscosity of the liquid we have in the case of chocolate versus water, creating a fountain 9 foot tall or no fountain at all, and so on. It's pretty cool. So hopefully you're enjoying it, stay positive, and thank you for watching this video. Like and subscribe.